Welcome to Student, a series of animated calculus videos that will help you prepare for the AP exam. These videos were made by students for students. Yep, that's me, Inspector Integral. You've probably heard of me. I'm a pretty well-known guy. Of course, in the detective business, that's not always a good thing. A guy like me has plenty of enemies. In fact, I had just taken down a gang of some pretty nasty derivatives, so I was pretty worn out. Unfortunately, my sleep was interrupted when my phone started ringing. With my cat-like reflexes, I woke up and grabbed the phone on its second ring. The client was talking too fast to understand, so I told them to take a deep breath and start over. After all, what did they have to worry about with a professional private eye on the case? Once they had calmed down, they told me about a murder that happened last night at the gym. I was intrigued. I had never investigated a health nut homicide before, so I told them I'd take their case. "I'll be right over," I said, and I got up to leave. On my way out, I noticed a mysterious envelope that someone had slipped under my door. Perhaps it was connected to the case? Maybe my client had slipped me some more information that I needed to read before I left. I decided to open it and find out. Inside, it had some pretty fancy math lingo. It looked like the work of a professional mathematician. This guy was not fooling around. I decided to take a closer look. It says something about lesson 7.8, which is apparently exponential models with differential equations. There are also a couple of other inconsequential things on here, but that's about it for this clue. Luckily, I have files on every calculus topic you could wish for, so I had no trouble locating my differential equations folder. Once I had the right file, it was a piece of cake to find the page I was looking for. I decided it would be a good idea to study up on this topic in case it had any bearing on the case, so I grabbed my magnifying glass and looked closer. So right here we have the differential equation for exponential models. It's important to note that the rate of change of y, that's dy dt, is directly proportional to y. And the k here is the proportionality constant, which is just a number, like 200 or negative a half or something like that. Down here is the general solution to the differential equation, which we call the sect model. The only new variable here is the c, which is the initial value of y. One important thing to note here is that exponential growth occurs when k is greater than 0, and exponential decay occurs when k is less than 0. Now, looking at this graph, it is some variable y over time. Let's say it's the amount of crime over an interval of time. Obviously, since I've come to the city, the crime has gone down, since I've sent so many crooks to the big house. Anyway, in these problems, it is very common to solve for k, whether analytically or graphically. Here, let's find k at time 6 by using the graph. We use the sect model and fill in our known variables by looking at the graph. Obviously, we know that t is equal to 6. The c, or the initial value, looks like it's about 32 up here. Finally, we can see that the y, or crimes, is about 12 at this time. Putting that all together, we would get this equation, which we could now solve for k. But I should really get back to the case, so I won't do that. With that spontaneous study session out of the way, I grabbed my coat and headed to the gym. Upon my arrival, I was shocked to see what had happened. It appeared that the murderer had used a barbell to take down their victim. Investigating further, I found 5 oddly marked scraps of paper. It was like the killer was trying to convey a message of some sort. I gently lifted the barbell and confirmed that its weight could indeed do some serious damage. I took out my portable camera and snapped a few photos of the crime scene. Once I was sure I had enough, I picked off the mysterious notes left on the body. There were the letters A, B, C, D, and E. It appeared as though the killer liked his alphabet. Leaving no stone unturned, I flipped the notes around and was surprised to find math on the back of them. Pocketing them for now, I quickly measured the temperature of the corpse and found that it had cooled down to 90.3 degrees Fahrenheit. On the way back to my office, I had forgotten all about the math hidden on the back of the notes, so I thought my only lead was some combination of these 5 letters. Once I had sat down and rolled my sleeves up, I got right to work on deciphering the clues I had found. Clearly, these letters meant something significant. I just had to figure out what. Perhaps they formed some sort of code where each letter stands for a number and you had to use them to solve an equation? Or maybe they were a name, but I didn't have anyone named Absidy on my criminal records, so that was another dead end. Minutes passed and I made no progress. That was at least, until my hand slipped off the wall, and I noticed another note in the envelope that I hadn't seen earlier. I unfolded it, and immediately the pieces started coming together in my head. It was a multiple choice calculus question, with answers A through E. I quickly got to work on it. So here's what the paper says. A rumor spreads among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model this situation with respect to time, t, where k is a positive constant? Right off the bat, we can eliminate answer A, since it is not a product of P, those who have heard the rumor, and those who have not heard the rumor. Now, we can write out our differential equation using the stem provided by the remaining answer choices. Again, we can eliminate more answers, since the problem is asking for the product of P, those who have heard the rumor, and those who have not. So, D and E can be crossed out since they don't have a P. Finally, we just need to think about whether it is B or C. So, we need to figure out what represents the number of people who have not heard the rumor, since we already have P here. We have the total population N, and we need to take away those who have heard the rumor, so we need to subtract P, which gives us B as our final answer. Now, if you'll excuse me, I have a mystery to solve. I made short work of that problem, and figured out that I need to go seek out Mr. B, since he supposedly has heard the rumor of who the killer is. Luckily, I knew just where to find him. I hurried to his usual hangout spot and found somewhere to hide, and just in time, there he was, holding a math book of some type. He passed by me in a hurry, as if he had been spooked by something. Or someone? Surely he hadn't seen me in my flawless hiding spot. I was thoroughly confused. But then, it hit me. Literally. Sometime later, I woke up, dazed and confused. I had a headache the size of the AP exam, and I could barely move. But even in my woozy state, my instincts were still sharp, and I noticed a book beside me. Little did I realize that this book held all the answers to this case. I stumbled back into my office with a bag of frozen vegetables on my aching head. I was in no mood to continue the case. My only lead had ended with a mild concussion and some asparagus in my hair. I had failed. Feeling defeated, I decided to look at the book Mr. B had dropped, because what else could I do? It looked just like any old math book I've ever seen. Nothing felt out of the ordinary about this dumb book, until I noticed a bookmark that looked eerily similar to the notes I found on the dead body. I felt a bit of hope spark inside of me. I opened to the marked page, and found that Mr. B had written one simple word on the note: Newton. Suddenly, my brain flared and everything started to make sense. I eagerly searched my notes until I found a page I was looking for. It was time to do a bit more research. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature in the surrounding medium. Now, on its own, that definition probably doesn't mean a whole lot to you, but looking at the equation, we can see that it is very similar to the differential equation from earlier, just with some added bits. The T represents the temperature of the object, so it would be like the body, in our case, while the M represents the temperature of the object's surroundings. I also seem to remember that this isn't explicitly tested in the AP test, but similar models have been, so I need to keep that in mind. But, back to the problem at hand. Feeling invigorated with this new knowledge, I quickly called up my friend at the gym and asked for a couple of temperature readings. Luckily, I had forgotten my thermometer at the gym, so it was easy for him to record accurate temperatures. After he gave me the readings, I got straight to work on the problem. So I've already written out the stem of our FRQ here, so we should have no trouble finding the answers. So a detective, that's me, Inspector Integral, finds a murder victim at 9 a.m. The temperature of the body is measured at 90.3 degrees Fahrenheit. 1 hour later, the temperature of the body is 89 degrees Fahrenheit. The temperature of the room has been maintained at a constant 68 degrees Fahrenheit. So A, assuming the temperature, T, of the body obeys Newton's law of cooling, write a differential equation for T. And then B here is solve the differential equation to estimate the time the murder occurred. So we can take 2 points out of this problem, which are 0, 90.3, and 1, 89, from our 2 temperature readings at different times, and we can start on A. So our differential equation will have the Newton's law of cooling model we looked at a moment ago. It has the rate the temperature changes with respect to time, dt, and that's set equal to K, the proportionality constant, times T minus 68, where 68 is the temperature of the room, the surroundings. And we're looking for the temperature of the body. Now we can solve this equation to find the approximate time of death. So let's do the separation of variables and integrate them. So we have the integral of 1 over T minus 68. The temperature is equal to the integral of K d time. Skipping ahead a bit, since we don't need to see all the math here, we get our sect model as T is equal to C e to the KT plus 68. That's just a simplified version of these, and we just kind of skip the math here. Now we can plug in our first point we got over here to solve for C, since K cancels out. And doing that, we would get C is equal to 22.3. We can plug that in now, the 22.3, and get an improved equation. So here it is. Using this equation, we can plug in our second point to find K. So then we would solve this, and we would get K is equal to negative 0.06. Finally, we plug in all our variables to solve for T. And in this case, the temperature is 98.6, which is the average body temperature. So we're just going to take that so we can approximate it. And when we solve for the time, we would get T is equal to negative 5.27. And if we interpret that answer, I ran out of room here, so I'm going to go up here, we get 5 hours and 16 minutes before 9 a.m., or time of death is around 3:44 a.m. We've done it! With that answer in mind, I can now solve the case.
So, I had determined that the poor sap's death happened at 3:44 a.m. I found that strange. My client had assured me that no one came into the gym after midnight, which meant that the victim would have been alone. Once again, I found myself examining the Newton note, and a startling revelation came to me. Maybe I had misinterpreted the note's meaning. After all, Newton is well known for his work on gravity. That was it! I had solved the mystery. Mr. B wasn't the killer after all. This wasn't even a murder to begin with. Some late-night weightlifter must have dropped the barbell on himself and couldn't get it off. It was as simple as that. With that case solved, I leaned back in my chair and took some well-deserved rest. Hopefully, I have sweet dreams, because this case was a nightmare. Some might even say it was Newton's nightmare.